Hello. So now that we're done with the the step response of second order with the different cases, we can now go and discuss the performance criteria. Performance criteria of that step response. What are the factors, the parameters that we look at when we are designing our system? So if we have here a second order system, let's take back this drawing. Let's copy this one and paste it here. So this is our response. This is an overdump response, step response of a second order. And our steady state value here is 1. So this is a unit step response. So now, what are the criteria or parameters that we want to know? The first one is the what we call the rise time. Rise time or TR. So what's a rise time? Rise time, this is for a overdump system. This is the time to reach steady state volume. To reach steady state volume. This is for an overdump, for overdump system or underdump rather. How about if it's for overdump? So for overdump, when the dumping ratio is greater than 1, then the rise time will be the time to go, the time to go from 10% to 90%, from 10% to 90% of the steady state value. Okay, so this is rise time. Now we will derive this. So in the drawing, the rise time for this is an underdump system. So the rise time is when the the time response reach uh, 1, which is our steady state value here. So if we, this is the 1, if we project this on the x-axis or the time domain, the time there is called the rise time. For an underdump or from overdump, for an overdump, so if this is the overdump system, the time needed to reach 10% of this, if this is 10%, up to 90%, 90%. The time needed here, and this one, this is the rise time. So from 10% to 90%. That's for overdump system. Also for a critically dump, because critically dump there's no overshoot. So now we want to derive the formula. So let's focus first on the underdump system. So based from the definition, if it's a unit step, let's take a unit step because this is a unit step response. The final value is 1, the gain is 1. Now, we already derived the response for this, y of t for an underdump system. We derive it here. So this is our final answer before. So let's just copy this. And paste it here. So to solve for the rise time, based from this equation, we just equate y of t be equal to 1. Because that's the definition of a time, rise time. So we equate 1 to this expression, then we will solve for the time. The time that we will be solving here will be tr. So let's do that. So this is 1 equals 1 minus e raised to that one. Let's copy this. Then we solve for t. Our t now here will be that will be our rise time. tr. tr. This is also so 1 and 1 will be 0. So this will be 0 equals this again. Let's copy this one. Then uh, we can also divide both sides by this e. So this will be removed from the equation, and this is negative. So we have 0 equals negative cosine omega d t plus zeta omega n omega d sine omega d t. Then this is also negative. It should be negative. We need to distribute the negative. And we can put cosine omega dt at the right side or the left side. Cosine omega dt will be equal to zeta omega n over omega d times sine omega dt. Then we can divide both sides by cosine omega d. So here omega n over omega d. Then we have sine omega dt all over cosine omega dt will be equal to 1. Or sine, or this is negative, should be negative. Sine, or sine omega d over cosine omega d, that's equal to, from the identities, that's just equal to tangent. Negative, then cross multiply, this will be omega d all over zeta omega n. Then taking the tangent inverse, so to solve for omega dt, remember the tangent is a is an odd function. So meaning if we take the tangent of a negative, it's equal to the negative of the tangent of its positive value. So we can just remove the negative here, then tangent inverse of omega d all over zeta omega n. Then, because we did the tangent inverse, we solve for the angle here. Did we have negative? So if we look at the plot at the time domain, there will be no negative value for our time response or our time because there's no negative time in control system. We don't deal with negatives. We only deal from zero of the time to positive infinity. So we don't have negative. So in order to remove that negative, there's so many uh, solutions for this one, for this angle. The next one will be the positive. So we can just add this one with half the revolution. So that we will be sure that the next one will be a positive one. And also, omega d is equal to, remember our formula of omega d. Omega d is omega n. Omega d is equal to omega n times the square root. This is for underdamped system. So we can use 1 minus zeta squared. So we can substitute this one here so that the omega n here and omega n here will cancel out. So we'll have omega d equals pi minus tangent inverse of, so what will be the remaining expression here? It will be just 1 minus zeta squared all over zeta. That omega n will cancel out because omega d is equal to omega n times the square root of 1 minus zeta squared. Then the time here, this t here now, we can name it t or rise time. And this will be equal to 1 over omega d of that whole expression, pi minus tangent inverse of the square root of 1 minus zeta squared all over zeta. So this is now the formula for the rise time for an underdamped system. For overdump, you need to substitute 10% and also 90%, then solve for t. Just like what we did here. Instead of 1, you will be substituting 0.1 and 0.9. Then solve for t at 0.1, solve for t at 0.9. So for overdump. So the rise time will be equal to you need to substitute y at 0.1, then y at 0.9. Substitute 0.1 and 0.9. So you have time at 0.1, time at 0.9. Then your rise time will be equal to that time at 0.9 minus the time at 0.1. So repeat the process again, but instead of using y's of 1, you use y's of 0.1 and 0.9. It's like what we did here. Then subtract that, and that will be our rise time for an overdump system. Then let's try to have an example to solve for the rise time for the underdump system. So let's use the SMOS to verify if our answer is correct or not. Then we will also use our formula to solve for the rise time, and we will compare if it's correct. The formula is correct. So I just open Desmos here. Then we can type again our equation. So we will be doing overdump. So we use overdump. So where's that overdump here? That's the one. Then so this will be y equals 1 minus e raised to, let's say again, our damping ratio to be equal to a, and our omega n to be equal to b. Then add a slider. Then you multiply it with d or x. Then this whole thing multiplied by cosine of omega d. Omega d is omega n, which is b times the square root of square root of 1 minus zeta squared. 1 minus, or zeta is a, so this is squared. So this is for the cosine omega d, then multiply it by x. Then plus zeta over times omega n over omega d. Zeta is a times omega n is b. Then divide this with omega d, and that is omega n. Oh, so magka-cancel. B will cancel out here. So this will be the square root of 1 minus a squared. Then you multiply it with sine of omega d is b times the square root of 1 minus a squared times x. Then, so that's our y's of t. Now we want to determine, we can put values for a and b. Remember, a is our a is the damping ratio, while b is the natural frequency. So we can set the value for the damping ratio. It should be less than 1, because we are dealing with an underdamped system. So let's say this is point 6. Then for the frequency, we can say this is equal to 5, or around 5. If we increase, we just decrease it to 3, 2, or okay, 3. So 3, or we can increase our value for B. We can also increase what's the better value? Okay, that's 0.2, and let's say this is 4.4. So this one. So we have an input y equals 1. So this is our steady state value. Should be our steady state value. Now at this point, this should be our rise time. So it's equal to 0.411 based from this graph. When, let's make this one 4. Okay, this one, 0.452. Now let's solve that one without using the plotting or of the Desmos, but using the derived formula here, this one. So remember, calculate TR, rise time. Calculate rise time if our omega n is equal to, what's the value again? 4. And our dumping ratio is equal to 0.2. I think 0.2. Yeah. So using the formula here, so rise time now will be equal to 1 over omega d. 1 over omega d is omega n. So let's solve for omega d here. Omega d is equal to omega n 4 times the square root of 1 minus zeta squared. 1 minus 0.2 squared. So this will be equal to 3.919. So omega d will be 3.9. 3.919. So 1 over 3.919 multiplied by pi minus tangent inverse of the square root of 1 minus 0.2 squared all over 0.2. Then let's calculate again this one. So remember, this is 1 over 3.919. Then you multiply this with shift pi minus shift tangent, because it's tangent inverse of the square root of 1 minus 0.2 squared all over 0.2. And this will be equal to 0. So TR is equal to 0.452 seconds. Let's try to look at graph again if it's 0.452. Where's that rise time? This one. So it's also equal to 0.452. So we have the correct answer. So the equation or the formula that we derive is the right formula. So that is 0.452 for the rise time. So you can use that formula, this formula here, to solve for that. Okay, so this is rise time. Next is the next parameter. We call it number 2. For underdamped system, we call this one the peak time. Peak time. There's no peak time for the overdump. We only have peak time for the underdump because there's an overshoot for underdump here. So peak time is the time needed to reach this point. At this point, the highest value that the response reached, and the time needed to reach that, we call it peak time. So this will be TP. So how do we solve this? How do we solve the peak time? So when we say peak time, the maximum value, that's the maximum value of y. So remember calculus. When we solve for the maximum and the minimum value, the optimization part, we can solve for the maximum value. How do we solve for the maximum value? With